All right, let's talk about graph problems. For a lot of us, just hearing those words in a technical interview can make your stomach drop. They feel abstract, complicated, and maybe even a little disconnected from what we do every day. But what if they're not really about memorizing a ton of different algorithms? What if it's all about spotting one single fundamental pattern? Let's dive in. And you know what? This sentiment is so common, and for a really good reason. If you're an experienced developer, it can feel like you're being quizzed on academic trivia that has almost nothing to do with building real software. It's a totally valid frustration. So, what's really going on? Well, here's what we're going to do. We're going to try to reframe that very question, because these problems aren't just about trivia. They're a test of a really crucial skill, your ability to look at a simple problem, something like a grid, and see the powerful underlying structure of a graph hiding inside. It's all about a shift in perspective. Okay, so to really see this pattern in action, we're going to break down one of the most classic interview questions there is. It looks simple on the surface, but trust me, it's the perfect key for unlocking this entire family of problems. Number of islands. You get a 2D grid, a matrix, full of ones and zeros. The ones are land, the zeros are water. An island is just any group of ones that are connected, up, down, left, or right. Your job? Count them up. Count how many separate islands there are. Seems straightforward, right? But the most elegant solution comes from not seeing this as a grid at all. And this, right here, is the absolute key, the aha moment. We're going to reimagine this grid as a graph. Think about it. Every single one is a node, or a vertex. And if two ones are touching, well, that's an edge connecting them. All of a sudden, the problem isn't counting islands anymore, it's counting the number of connected components in a graph. And for that, we have some seriously powerful standard tools at our disposal. So, once we see the graph, the next logical question is, how do we explore it? How do we actually walk from one piece of land to the next to map out an entire island? Well, there are two main strategies for this, and understanding the difference between them is crucial. Now, this is where it gets really interesting. The only real difference between these two is the data structure they use, and that completely changes how they explore. Breadth first search, BFS, uses a queue. Think of it like dropping a rock in a pond. It explores level by level, like a ripple spreading out. It's perfect for finding the shortest path. Depth first search, DFS, uses a stack. It dives as deep as it possibly can down one single path before it backs up, exploring more like a snake slithering through a maze. Now for our island problem, we just need to find all the connected bits of land. We don't really care about the shortest path or anything fancy, so honestly, both BFS and DFS will get the job done. But we're going to start with the recursive version of DFS because it's usually what people think of first, and it's a perfect way to show some of the most common and dangerous traps you can fall into in an interview. Okay, so you're feeling pretty good, right? You spotted the graph, you picked an algorithm, recursive DFS, but this is the exact moment where a lot of candidates stumble because the most obvious way to write this code has two really critical weaknesses that can literally crash your program. And here they are, the two big killers. First, checking a cell that's off the grid, which immediately throws an error and stops your code cold. And second, something a little more sneaky, the stack overflow error. This one happens when your recursion just goes too deep, and it is a classic way to fail grid problems. Let's unpack that for a second. Every single time your function calls itself, it adds a little frame, like a plate, onto something called the call stack. Now, imagine a huge island that's just one cell wide, but thousands of cells long, a big snake. Your recursive DFS is going to follow that path, adding a plate to the stack for every single cell. The problem is, the system stack of plates isn't infinite. Eventually, you run out, and the whole thing comes crashing down. That's a stack overflow. Okay, so we've seen the traps, but don't worry. The good news is, fixing them is how you demonstrate that you write robust, professional-level code, which is exactly what interviewers are looking for. So let's pivot to the solutions. This looks so innocent, but it's a fatal flaw. Just look at the order here. The code tries to read what's at grid R, C, before it checks if R and C are even valid numbers. So if R is, say, -1, the program tries to access an invalid spot in memory and just crashes right there. It never even gets to the part that checks if it's in bounds. And the fix is just so elegant. You just flip the order. By putting the boundary checks first, you take advantage of something called short-circuiting. If that very first condition, 0 less than or equal to r less than rows, is false, the program doesn't even bother to look at the rest of the line. It knows the whole thing is false, so it just stops, and you completely avoid the crash. It's clean, it's safe, it's the professional way to do it. All right, now for the big one, that pesky Stack Overflow. How do we get around it? Simple. We basically do what the system was doing under the hood, but we do it ourselves, manually. We replace that hidden, limited call stack with our very own stack data structure that we control. This is what we call an iterative approach. And you know what? The pattern is beautifully simple. First, you just create a stack. Then you push your starting cell onto it. After that, you just loop. As long as there's something in the stack, you pop a cell off, you process it, maybe you mark it as visited, and then you push all of its valid unvisited neighbors right back onto the stack. You get the exact same snake-like DFS exploration, but with absolutely zero risk of a stack overflow. Now, getting the right answer is step one. But what often separates a junior from a senior candidate in an interview? It's showing that you understand performance. Writing code that works is one thing. Writing code that works efficiently is the real goal. So to talk about this, we use something called time complexity, or Big O notation. It's just a way to describe how our code's runtime grows as the input gets bigger. For our grid, V stands for vertices, which is just the total number of cells, and E stands for edges, which are the connections between them. It's just a shared language to talk about speed. Here's the beautiful thing. A correctly written BFS or DFS is incredibly efficient. The key, the secret sauce, is that you visit every single cell and every connection only one time. You do this by keeping track of where you've already been so you don't do the same work over and over. This gives us what's called a linear time complexity of OV plus E. Long story short, it's blazing fast. And if you think this is just theory, let's put some real numbers on it. An interview problem might give you a 300 by 300 grid. That's 90,000 cells, 90,000 vertices. Our efficient O of V plus E algorithm chews through that no problem. But an inefficient approach, maybe something that is O of V squared, we're talking 90,000 times 90,000. That's over 8 billion operations. Your program isn't just slow at that point, it's completely dead in the water. It'll time out for sure. So, let's pull this all together. What are the key things you need to remember? 1. See the pattern. So many problems, grids, word puzzles are secretly graph problems. 2. Know your tools. BFS for shortest path ripples, DFS for connectivity snakes. 3. Avoid the traps. Always check your boundaries first and use an iterative approach for large grids to dodge stack overflow. And 4. Always aim for that optimal OV plus E runtime by tracking where you've already visited. Because at the end of the day, the test isn't really about whether you memorize the steps for DFS. It's about whether you can make that critical leap of abstraction to see the hidden structure. Once you see the graph, the solution becomes almost standard. So the real question to take away from all of this is, what other problems have a graph hiding inside them, just waiting to be found?